My name is Ron Pressler. I'm the founder of Parallel Universe. We make an open source server-side stack for the JVM that helps you write very efficient applications. So the talk today is kind of messy. It's going to be part rant, part opinion, part some rehashing of old ideas. I am going to talk about functional programming and imperative programming. I am not going to discuss the relative merits of the two, but I am going to discuss the applicability of certain pure functional concepts for imperative languages, or rather lack thereof. And this entire talk is given from the perspective of an imperative programmer. So I'm not going to use the right names for things, or the names Haskell gives them. Yeah, we are going to discuss monads, and I'm going to explain what they are, and then why they're absolutely terrible. Not for imperative languages. For imperative languages, they're excellent for pure functional. Okay, so as a motivation, these are three classes from the JDK. This is a standard Java runtime library. Many of you must have heard that Java 8 now has lambdas. It also has, in the standard library, at least 3 monads. This means that there are more people using monads in production now in Java than anyone using Haskell for anything by probably orders of magnitude, which makes Java the most monad-heavy language in existence. Now, it's not just Java. Java itself, this is built into the libraries, but there's a very good family of libraries called ReactiveX that's based on monads for various languages. Their promises are based on monads in JavaScript, and recently I think Facebook introduced C++ futures, which are the same idea for C++. Okay, so we'll start by first going back to basics and defining a pure function. So a pure function is a subroutine that behaves like a mathematical function, which means that its only inputs are its arguments, and its only output is its return value, and it's not allowed to change any externally observable state or do any I/O whatsoever. Just takes parameters, compute results. Unfortunately, we have a lot to cover. Keep your questions to the end. I hope we'll have time because there's a lot to go through, and the best part is in the end. Okay, so pure functional languages means that all of our subroutines are pure. And as a consequence of this, or the converse, is that if you are not pure, then you are imperative. Even functional languages like Clojure, Erlang, Scheme, ML even, are imperative. So in this, I'm going to treat them as imperative. We'll see why. But an imperative programmer can then ask themselves, then if all of my subroutines are pure functions, how can I do anything useful? If none of them is allowed to do any I/O, how can I achieve anything useful? And monads is the answer to that. So monads are what gives pure functions superpowers. Now, from the perspective of an imperative programmer, I know PFP people have mathematical terms for everything. We don't know about that. So from an imperative programmer's perspective, a monad is a design pattern. And it's a design pattern that's made of 3 parts. First, the monadic value. Monadic value takes a simple value, say the number 3, and wraps it in a context. A monadic function is a function, a pure function, has to be because we're pure languages, that returns a monadic value. And the composer, again in Haskell it's called bind, the composer takes a monadic value and composes it with a monadic function. And together you can form a chain of monadic functions. Each of them returns a monadic value, and the composer changes it to the next. This way you create a sequence of computation steps, and we'll see how all of them together can do something useful. So to make it more concrete, let's introduce a simple monad. I call it the square brackets monad. It implements a counter. So our monadic value is going to be the simple value x in the square brackets context, along with an integer. And this is our monadic function. It takes simple value x, returns a monadic value, y and k. And then, this is the interesting part, the composer. And here I denote it as the name of the monad in a circle. So it takes a monadic value x and n, and composes it with a monadic function f. How does it do that? What is the composition rule for this particular monad? So it's going to take x and apply it into f, and then f is going to return y and k, and then the composer is going to take the k and add it to the original n. So it accumulates. Let's see it working in a more concrete example. So suppose we have these three functions. They're pure functions. They're monadic functions, right? They return monadic values. And we chain them with composers, and I claim that the answer is 8 and 6. We'll see why. So we start with z, doesn't take any arguments, and returns 3 and 1. And then we compose that with f. So it takes a 3, passes it into f, and then f returns 4 and 2. And then we add the 2 to the original 1, and we have 4 and 3. And then we take that 4 and 3, compose it with g, and we do that by taking the 4, passing it into g. G returns 8 and 3. And then we take the 3, add it to the 3 we had, and the final result is 8, 6. Another more real-life example is exceptions. Pure functions, like I said, they can't throw exceptions. They can't do anything other than compute or return value. But with monads, we can simulate exceptions. Now, what are exceptions? In an imperative language, if you have a sequence of computational steps and one of them errors, then we abort the computation and we don't execute the subsequent steps. So we can do that with a monad. I call it here the angle brackets monad, and the monadic context in this case is E, which can be either success or error. And f is going to be, as before, our monadic function. And what is our composition rule? So suppose we have the monadic value x and e, and we want to compose that with f. So if e is success, then we pass x into f and return that result. If e is error, we never evaluate f and just return error. So how does this work? Suppose these are our monadic functions, and we chain them together. So z would return 3 success, which means that we take the 3, pass it into f. F returns 4 success. We take the 4, pass that into g, and g returns error. At which point, the composition rule is not going to evaluate anything. It's not going to evaluate h in this case and just return error. Okay, so it works just like exceptions. Finally, how do we do I/O with just pure functions and pure values? So in this case, our context is going to be an operation, an I/O operation that's added to the simple value x, and that operation is going to be one of print, read, or no-op. There has to be a no-op because there are rules to which compositions are legal or not, but that we don't care about that for the moment. So how do we compose op x with f? So if op is print, the composition rule is going to print x to the console and evaluate f with no parameters. If op is read, the composition rule is going to ignore x, read a string from the console, and pass that into the next function in the chain, into f. And if op is no op, then we just take x and pass that into f. So what can we do with that? We have these 3 monadic functions, and we can compose them. So p is going to return print and what is your name, so the composer is going to print that to the console. Then R is going to get called with no arguments, and it's going to return read. So the composer is going to wait for input, and the user is going to input their name, and then the composer is going to pass the name to n, and n is going to return print hello and the name, and the composer is going to print that. So this way, and now you can ask, okay, but if a composer is a function, how is the composer allowed to do any I/O? And the answer is that this particular composer is not written in the pure functional language. It's built into the runtime, and so therefore the same restrictions don't apply to it. Another thing you may ask is, okay, but now if I have a function that has this p, r, n sequence, then this function enclosing this is now doing I/O. And pure functional languages, this is why they don't let you evaluate this in place. Any function that wants to call this sequence has to return this expression as its return value all the way up to the main function of the program, and then it returns to the runtime, and the runtime evaluates it lazily. But this is a detail that we don't care about. And then, okay, so now you ask yourself, fine, okay, so we know what monads are. We clearly understand why they're important for pure functional languages, but why does Java have them? And how come Java uses them so much? we can throw exceptions, we can change state, we can do I/O. So to understand that, we look at the previous example, how it would be written in an imperative language. So this looks kind of familiar and boring, but I would claim that just as the monad is like the uber abstraction of pure functional programming, what we see here isn't trivial at all, and actually touches at the essence of what imperative programming is. And what's interesting about this is not that we're allowed to do I/O in place or have effects, but what happens when we call R. When we call R that reads input from the console, our program pauses. It suspends itself. What happens then? We don't know and we don't care. Usually we yield control over the CPU to another program to run. And once that input returns, then we continue with our computation. And this is the concept of the thread, of doing one thing after another and potentially blocking, is what I like to claim the essence of imperative programming, not the ability to change global state, but that. And I'm going to prove it to you by showing to you what happens when we take that away. And I hope you'll agree, at least that this is what imperative programming is all about, the ability to block threads. And the thread, let's define it a little bit just to make you think about the same thing that I'm thinking of, is just a sequence of operations with a stack that can block. It is also a unit of programming concurrency in the sense that you can have multiple threads running, but even if your programming language doesn't support multi-threading, and you only have one thread, say, I think Ruby, then it still uses the thread abstraction. Also, because I mentioned the word concurrency here, and I'm going to mention it again, let me just say that I'm not talking about a particular concurrency model. I'm not talking about shared state concurrency. I'm just talking about a concurrency model concurrency that allows multiple blocking threads to run at the same time. How they exchange information is completely orthogonal. They can be shared nothing. They can exchange messages. Okay, so to make this so we can follow and see what happens, how monads destroy imperative languages. So let's suppose we have this web application that needs to perform some financial computation on behalf of the user. And in order to do that, it uses a very simple API that consists of a single function, single method. This is Java syntax. That's called compute, and it's going to take the name of the financial operation and a single argument and return the result. In this case, we put it in a function called calc important finance, and we do all that. But the thing to notice here about compute is that in order to compute the result, might need to consult an internal service. For example, to figure out, to retrieve the current exchange rate from the US dollar to the euro, or the current interest rate. So compute may take a long time, may do I/O, and can block. But we don't care about that, right? Because we're imperative programmers, and this is just a sequence. It's very clear what's going on here. But herein lies the problems with threads. And the problem is, I think, best summarized by this equation. It's called Little's Law. Actually, proving it is more complicated than it seems. But it says this. If we have a server that's serving requests, and it takes us a certain amount of time, called W, on average, to service each request, start to finish. And remember, requests in these days can take a while. It can be an open session, like an open TCP socket that communicates for a while. Then, if our incoming request rate is lambda, then we must support at least L level of concurrency. And this level of concurrency is imposed on us by the domain. It says that the number of pending messages that our server needs to support is L. If our server's capacity is below L, it's going to become unresponsive and crash. So we must do that. And there are various factors affecting our server's capacity. So, for example, one can be the maximum number of open TCP connections, right? We can't, so that's, if the L is bigger than the number of maximum open TCP connections, we're just not going to be able to handle the load. But that number is pretty large. On modern Linuxes, you can support maybe up to 2 million concurrent open TCP sockets. But a number that is not so large is a number of threads. Modern operating systems can support up to somewhere between 5,000 and 20,000 active threads that do some work occasionally. And this number is pretty low and puts like an upper bound on how high we can go with concurrency. And that means that if we use compute as we did before, and for each request we handle it start to finish on the same thread and block, then we're quickly going to run out of threads. And that means that we're not allowed to block, and we must use fewer threads, fewer softer unit of concurrency to support the domain concurrency. So we can't block, and we can't use our super abstraction. So what happens? So first, we said, okay, so we have this thing called asynchronous I/O. We don't have to block a thread. And we'll have a thread sitting somewhere. It's going to pull the OS's I/O queue. And when our I/O operation is going to complete, it's going to call a callback. We say, fine, okay, so compute now, instead of returning a result, it'll take a callback, pass it on to the I/O thread, and once our result is ready, our callback is going to get triggered. And this is the result. It gets unwieldy very fast, and yeah, it's just not good. It looks like Node.js, right? So imperative programmers just lost their ability to use a very important abstraction. I haven't proved yet that it's the most important abstraction, but I think you'll agree it's a very important abstraction, the blocking thread. And our only option was not to block, and callbacks, are terrible. And it was in this sorry, sad, and confused state that the PFP people found us. And they said, you know what? Instead, don't return a simple value from compute, because for that you need to block. But don't take a callback either. Turn compute into a monadic function. It'll return a value in a context. Now, in the case of Java, it's called a completable future. We'll just call it future. Some people call this the future monad. Some people call it the promise monad. Some people say that it's not a monad at all, just something that looks like a monad. But again, we don't care. It looks enough like a monad. And the idea of the future is that the wrapped value is not immediately available. It will become available when let's say the I/O thread sets the value and completes the I/O operation. And therefore, our composition rule, which in the Java it's called then compose, says that when the I/O thread sets the value of the future, we're going to pass that to the next monadic function in the chain. And they said, okay, listen, now your code is going to look like this. And this is Java 8 code. And I think you'll all agree that it's much, much better than callbacks. If we have these three chained computes, we have the composer between them. You say, okay, Java doesn't have a nice syntax for monadic composition. Maybe it's solvable. It's fine. Now, I claim that this is absolutely terrible and not much better than callbacks. And let me try to convince you why. So first of all, suppose we want to encapsulate this computation in a function as we did before, calc important finance. How do we return the value from calc important finance? We can't extract the value out of the future, out of the monadic value, because it's not there yet. We could block, but that's exactly what we're trying to prevent. So we have two options. We can return the future from the function, or we can call a callback and publish the result. And those are our only two possibilities. And if we use a callback and then we're back to callbacks, if we return a monadic value, we'll quickly find that the entire call stack, all the way up, is infected with this monadic value. So now Java, we have to use monadic functions everywhere, pure monadic functions. Another thing, control flow. Suppose that we wanted to repeat a part of the sequence multiple times until we get the desired results. So for that, the imperative language gives us loops. Pure functional languages don't have loops, but we do. We can do that. It's very simple. How do we do that in monads? We can't. I mean, we can, but we have to use a monadic library. We have to use recursion and all kinds of stuff that pure functional languages do, but we don't have to. So yeah, so we can't use the call stack as we used to, and we can't use control flow the regular way. And finally, let's look at exceptions. So in the beginning of the talk, I showed how monads can simulate exceptions, and this particular monad does that too. So if one of the calls to compute errors and returns an exception, then the subsequent steps are not going to get evaluated, and this final lambda is going to get called with an exception. But this treats exceptions as value. The compute is not allowed to throw the exception because monadic functions are pure functions. It has to return the exception wrapped in the future. So you can't use throw. And over here, as you can see, we can't use catch either. You get the exception as a function argument. And the pure functional people are going to say, that's great, an error is a value. But to us imperative developers, an exception is more than a value. It's a value with a stack context. So when we log this to the log, and we're going to try to do post-mortem debugging, we're not going to see that the exception came from the calc important finance, from the call to the calc important finance method. Our stack context is lost. Yeah, in imperative languages, pull is always better than push. Unfortunately, I don't have time to get into that. But to summarize, monads make us, in imperative languages, again, monads make us throw out our old APIs to use monadic APIs, and they're viral. They infect the entire call stack. Second, we have to recreate everything the imperative languages always gives us, anyway. So we can't use for loops. We can't use while loops. Ifs, I think we can use. That's about it, because pure functional languages do have if. And we can't use exceptions. So all of that, error handling and control flow, has to be handled in this monadic language that is not part of our imperative language. And finally, we don't have the stack context for post-mortem debugging, and perhaps not less important than that, profiling. Suppose you run this program through a profiler, and you see that compute takes 95% of the runtime for the program. They say, okay, but is it when compute is called from calc important finance or calc future apartment value? You don't know that. So you can't even get the performance profile of the program. And this is something that's very important to imperative programmers. Now, it's not to say that monads are never useful in imperative languages. In fact, in some use cases, they're extremely useful, specifically when we deal with data parallelism. So monads give us a very nice way to say we have a huge blob of data and we want to do a following sequence of computation on it. And this is implemented in Java with Java 8 streams. And there, because we do operations in parallel, we explicitly say we don't care about the thread context, right? Because if we have a function and we tell the library run it on any thread because we want it to run in parallel, we don't care about the thread context. So for that, monads are very useful. So my question is, why replace a good, familiar, natural abstraction just because the implementation by the OS is inadequate? And in fact, it's not just a good abstraction. It is the core abstraction of imperative programs. Because imperative programs give us stacks, they give us control flow, and we can't use them, and exceptions, and we just can't use them once we start using monads. We have to basically rebuild Haskell in Java, and Java doesn't have the syntax for that, and it doesn't have the assurances, the pure assurances for that. Why can't we just fix a down implementation? And we can. And it turns out that it's quite easy. Instead of relying on the operating system to implement threads, we can implement them in the language runtime. This is called fibers, or user mode threads, or lightweight threads. And this is, and the way this is done is the language runtime can implement threads much more efficiently than the operating system. If you want to ask later why, I can explain in detail, but the idea is that those threads don't need to be as general as kernel threads, so we can do them much more efficiently. And in fact, this has been used very successfully in Erlang, yes, and in Go, and in Quasar. Quasar is our own open source library that adds true fibers to the JVM with no need to change the JVM. And now our code looks like this. Just as before, we can use the same old APIs we used to. And we're not limited by the number of threads. Because these threads are not kernel threads, they're not expensive. You can have 1 million of those. So threads, the number of threads, is no longer the bottleneck to Little's Law. And if you say, okay, but I like monads because they let you compose these nifty functional operators like filter and map, etc. You can still use those. Functional is great. So again, this is an example from Java and Quasar. So you subscribe to a channel and you attach a filter and a map on the numbers coming into the channel, but you consume the channel by looping and blocking on receive pulling out the messages, and you have all the advantages of both functional and imperative. You get your stack context, you get your profiling information, and none of the disadvantages. Now, fibers aren't perfect, especially for runtimes that don't support fibers natively, like the JVM. They do require library support. The libraries have to be aware of them. Luckily, it's very easy to wrap a library to support fibers without, while maintaining the API without changing you just wrap it. Debuggers, it can work with fibers, but sometimes if you step over something that blocks, it doesn't recognize that. You'll see a jump in the program, but you can just fix the debuggers. Again, it's not hard. But you do need to take care when you exit the runtime. Because the fibers or threads are implemented in the runtime, it's not in the kernel, once you exit the runtime and say call C, then then C is no longer aware of how those threads and stacks are implemented, so you have to be careful. Okay, so we've seen, so we can use our go back to our old habits. Threads are no longer a problem. Every incoming request, you can have 1 million of those. Each of them might take half an hour. You can write blocking code, get all the performance that you got with monads, you get your control flow, you get your exceptions, everything is fine. But something still bothered me a bit, and he said, but you know what, monads are really beautiful. Not imperative languages, in pure functional languages. They're a really beautiful, like basic abstraction. Can we have the same thing, something as essential in imperative languages? So before we get to that, let's think for a little while longer about the thread. So I said that the thread is the core concept. Now, that's not exactly true because a thread isn't fundamental. A thread is two things, really. It's a continuation. Now, if you know, a continuation is just a call stack. So a thread is the call stack with our local variables and the entire chain of calls that can block and resume. And the scheduler is what assigns our code or our continuation to a CPU core when it's ready to run. So the scheduler is not really important to the abstraction. It's just part of the implementation, and the code we write is not dependent on the scheduler. So the fundamental idea, the basis of imperative programming is the continuation or the call stack. So let's build on that. And here I'll introduce something called scope continuation. It's not really new, I think. It's a specific kind of something called delimited continuation, introduced in the mid-'80s in Scheme by someone who I think is at this conference. And let me explain how they work and show examples. So we need three things. We need a scope variable, which we're going to denote like that. For now, think of it as a thread local. We're going to introduce a keyword called cont that takes a routine and makes it able to pause and resume at any stack depth. Now, this is very important. We have to be able to pause at any stack depth, and this is why this is not the same as C#'s async await or Clojure's core async go blocks. They only let you pause at the topmost stack frame, and they're therefore called stackless continuation because they don't really support the stack. And finally, the pause operation is going to set the value of the scope variable, this kind of thread local, and jump to the point where cont was called. We'll see an example. Okay, so we have this context, this scope, and this scope belongs to the x scope variable. And here we take a function c, we turn it into a continuation, and we loop until it's done. Every time it pauses, we loop again until it completes. C itself just simply calls f twice, and f pauses twice. Once it sets the value of x to 3, and the second time to 5. So all in all, before C completes, it's going to pause 4 times, setting the values of x to 3 and 5 interchangeably, alternatively, and this is when it's going to print out 3, 5, 3, 5. One more thing about the scopes, they can be nested, and again, this is very important when we get to composition and how we do it better than monads. So suppose we have this x scope, and then inside it a y scope, and inside another x scope, and inside a continuation C. And C calls pause on the x scope. So C is going to jump to the innermost x scope that surrounds the continuation. So it's going to jump here and not there, because this is the innermost scope. Once it pauses on y, it's going to jump to the innermost y scope. So it's going to jump to this point, because this cont contains a continuation where the pause was called on y. Okay? And now let's implement exceptions. This is all our language doesn't have exceptions. Now we'll implement exceptions. This is like a pseudo syntax. It's actually quite similar to Kotlin. So we'll implement try and catch like this. Try is just going to be a function that takes two blocks, body and catch. And it's going to introduce the EX context. The EX is the scope variable. And it's going to turn the body into a continuation. And if it's not done, namely it paused, then there must have been an exception. We grab the value of the scope variable EX, put it into a local E, and if it's not empty, we invoked the catch block. And this is very important. We'll come back to that in a second, that we invoke the catch block outside of this scope. Else, if C completed normally, we just return this value. And we introduce the function scope. It's a regular function, and it calls pause and sets EX to the exception. So what does the code look like? Just like this. In fact, in Kotlin, you'd have even nicer syntax, but I wanted to make this clear that these are two blocks that you pass through the function. This is the body, and this is the catch block. And A might throw an exception. So what happens here when you throw an exception? When you throw an exception, we're going to, where was it? Yeah. We're going to jump here, and we see that it was in the middle of the run, so we'll grab the exception, and then we'll call the catch block. And what does the catch block do? Sorry. The catch block logs the exception and rethrows it. But now it rethrows it from outside this enclosing context, this enclosing scope. So the second time we pause we throw in the catch block, it's going to get caught by an enclosing scope. And it works just like exceptions. Okay, another example, generators. I think Python has them. A generators is you have a function that calls a yield or produce a value, and every time it's called, it's like it lazily adds another element to a collection. So we'll implement an iterator with a specific implementation that we call co-iterator, and the iterator's next method is going to introduce the element scope, and it's going to take the generator function, turn it into a continuation, and as long as it's not done, it returns the current value of the scope variable. And we have the produce function that pauses and sets the element to the given element here. And how do we use that? So, for example, this is the range function, and returns an iterator of a collection or a sequence of numbers between A and B, and it's simply a for loop that calls produce with every number. And this is produced lazily. We could also have an infinite range. And with that, I'm not going to go into details because I think I'm out of time. But you can implement flat map and filter, and they are very, very simple. One thing I do want you to notice here is that with monads, the flat map, if you know this, if not, it's okay. Flat map is the composition rule for the sequence monad, or the list monad. So you must implement, and that is the only thing the composition rule knows how to do. So you must implement map and filter in terms of flat map, because that is the only monadic value the composer accepts. That's the only thing. The composer can only do one thing. Here, that's not the case. Our composition rule is partly in the wrapping context and partly where we call pause. And this is why we can implement map and filter directly and flat map all to use the same context without interfering with one another. Every time we call produce in a loop, you can think about it as another time the monad evaluates the next function. So how, this may not be clear, you have to think about it later, but how do they compare? They're almost duals. So with a monad, a function returns a monadic value, and it's a hint to the composer how to apply the next one. Maybe many times, maybe never. If it's a filter or an exception, the composer decides. With a scope continuation, the inner code, the function, like the throw, the produce, that we called at the bottom or top of the stack, the innermost frame, directly decides how the next stage will be executed with pause. Every time we call pause, it's like evaluating f again, the next step. And it also decides at which scope to talk to. It's like the monadic value saying, this enclosing monad, don't listen to me. I want another monad to listen to me. And this gives us great composition. So we can have the try scope, and within it, the co-iterator scope, and anything in here, so the range can call produce, or a filter can call produce to produce another element for this scope, but it can also call throw. And if it calls throw, it's going to get handled by the outer scope. So these things compose perfectly. With monads, it's not exactly the case. You could think of a universal monadic value. I guess you could do that in closure, that you take the simple value, and the context is a map. And it says, my exception context is this, my IO context is that. And if the composer cares about this particular key in the map, it's going to handle that. If not, it's going to ignore it. But the problem with that is that it doesn't type check. And especially Haskell is a very statically typed language. So it uses something called monad transformers. First of all, they don't really always apply, and they're very, very hard to think about. I don't know if you've seen NASA's guidelines for writing safe C programs say that you can use a single pointer indirection or a double, like a pointer or a pointer to a pointer, but not a pointer to a pointer to a pointer. That's too much. Like 3 levels of indirection is too much. And I think the same applies to higher order functions. So we can handle first order functions or higher order like second order functions, but not third order. And not a function that calls a function that calls a function. And monad transformers go up as 4 or 5. And it's very, it's just hard to wrap your heads around, especially if you're an imperative program. And finally, these scopes type check, and they type check perfectly. So they compose perfectly, and they type check perfectly. With what type checker? With Java's checked exception type checker. So we can say that every function that might pause on a certain scope will declare that it pauses on that, like a Java checked exception. So f pauses, say, on exception. And the compiler is not going to let us to call f outside of a try context. And what's the signature of try? So f says, OK, I pause on exception because I might throw an exception, and on something else. Say I might produce a value. And try, the try type takes away the exception. It no longer pauses on exception because it catches it. It only pauses on the other things. So they compose perfectly, and they type check perfectly. So the PF people are going to say, yeah, but you have now continuations, and you have thread locals, and pause, and a lot. We just have pure functions, and that's true. You can't beat pure functional with economy. But in this case, we preserve all of our built-in constructs, and they compose perfectly, and they type check if you care about that. And with that, I'll finish. Thank you. If you have any questions, I just want to leave this up. I think it's a great tweet I just saw recently. It certainly applies to, I don't know if I'm the best programmer, but it certainly applies to me. Do we have time for questions? Yes.
So I really wonder how your approach compares when you try to cherry pick other monads, because monads, as long as you have abide to the rules of composition, you have semantics. And of course, you can cherry pick like collections and exceptions and come up with a custom system that kind of does the job well. But monads provide like a sound guarantee of providing as soon as you abide to the laws. And then you can use it for many, many other things. You can use it for probabilistic calculations. You attach any context you want to your computation, and you carry it around. But I don't see how you can destroy monads' powerfulness by showing 3 cherry-pick examples that solve 3 different examples. They're not solving the sound composition. You're not saying your approach composes well for 3 cherry-pick examples. Does it compose better than monad transformers when you only reply what to that?
Okay. So let me just say that again. The question is, you've just shown a few examples. How do we know that it's really more powerful? First of all, my claim is not that it's more powerful than monads, even though I think it is. And it's also not to tear apart monads. If you work in a pure functional language where you don't have loops and you don't have states and you don't have exceptions, you don't have I/O, then monads are your only way, and they're beautiful. It's a beautiful abstraction. But if not, I'm saying another beautiful abstraction that you can do in imperative languages. Now, it's true, I haven't proved rigorously that you can take any monad and implement it with scoped exception. My intuition says that you can. I just thought of it a few days ago, but my intuition says that you can. Every call to pause is like another application of the next monadic function. This is something I have to work out, but I think that you can prove that it's a strict superset of anything monads can do. About composition, again, I'm not saying it composes better than monad transformers, but monad transformers are harder to understand. I mean, I don't think Java is going to get monad transformers. I think ReactiveX has some, but they are very hard to understand. And again, my intuition says, and you can think about it more, we can talk about it later, that the ability to directly, when you pause and set that scoped variable is like setting the monadic context. And because you can talk to various enclosing scopes at the same time, you can say, now I'm talking to this one, I'm talking to that one. It's like the ability for a monadic function to talk to various composers, to various binds at the same time. It says, now I'm talking to you, now I'm talking to you. And I don't think it's possible with monads, unless you use the universal monad, but that is not statically sound. Yes.
So I think. I think another interesting point of comparison is the notion of coroutines that you have in beta. This is back in '75, so it's even before those delimited configurations, and I believe you may have hinted at Olivier Danvy, who introduced them. But these coroutines, basically, in beta you would have a component which is a special kind of object that will delimit the stack, so you can stop your execution, suspend to that point, you can resume it from there, and you can talk to that component. So the missing bit there is that in beta you do not have support for searching down the stack for the nearest enclosing component of a particular type such that you can read this scope variable. Right. And it would actually be interesting to add that.
I forgot to say that what I've shown about scoped continuations is going to be in Java, Java 9 probably. We already have working with an unmodified JVM working example for Java 7 and 8, but it's not as transparent. It's going to work transparently in Java 9. Yes?
So they're called scope continuations, but from the few examples, I couldn't tell what the scope was. Like, are they lexically scoped? How do you know?
They're lexically scoped, yes.
Okay, so do you declare it at the top, or?
Just like exceptions, just like the try block with exceptions, exactly the same.
But so there was another piece of code that is referring to the same name, which is declared in a parallel piece of code. So
right. So it's just like, think about it as two enclosed try blocks on the same exception type. So if you
so C uses X, which refers to the X that's up there, but how do you?
No, to the X and to the nearest one, just like exceptions. So if this one catches illegal, I don't know, number format exception, and this one catches illegal number format exception too, then when you throw it from here, it's going to be caught by the nearest enclosing scope, the innermost enclosing scope.
And then at runtime, it's thrown from the nearest, but I mean, C uses the name X, right? It writes.
Well, that's syntax. Think the way it's implemented. So X is not really X is a global name. Think of it as a type name.
So
it's actually implemented as a type name. I just didn't want to introduce types here.
Okay. All right, that's fine. That was
so each of these scopes is actually a type, like catch, like try and catch for a certain exception type. Okay. So thank you very much. let's see it working in a more concrete example. So suppose we have these three functions. They're pure functions. They're monadic functions, right? They return monadic values. And we chain them with composers. And I claim that the answer is 8 and 6. We'll see why. So we start with z. It doesn't take any arguments. And returns 3 and 1. And then we compose that with f. So it takes a 3, passes it into f, and then f returns 4 and 2. And then we add the 2 to the original 1, and we have 4 and 3. And then we take that 4 and 3, compose it with g, and we do that by taking the 4, passing it into g. G returns 8 and 3. And then we take the 3, add it to the 3 we had, and the final result is 8, 6. Another more real-life example is exceptions. Pure functions, like I said, they can't throw exceptions. They can't do anything other than compute or return value. But with monads, we can simulate exceptions. Now, what are exceptions? In an imperative language, if you have a sequence of computational steps and one of them errors, then we abort the computation and we don't execute the subsequent steps. So we can do that with a monad. I call it here the angle brackets monad. And the monadic context in this case is E, which can be either success or error. And f is going to be, as before, our monadic function. And what is our composition rule? So suppose we have the monadic value x and e, and we want to compose that with f. So if e is success, then we pass x into f and return that result. If e is error, we never evaluate f and just return error. So how does this work? Suppose these are our monadic functions, and we chain them together. Pure functions, superpowers. Now, from the perspective of an imperative programmer, I know PFP people have mathematical terms for everything. We don't know about that. So from an imperative programmer's perspective, a monad is a design pattern. And it's a design pattern that's made of 3 parts. First, the monadic value. Monadic value takes a simple value, say the number 3, and wraps it in a context. A monadic function is a function, a pure function, has to be because we're pure languages, that returns a monadic value. And the composer, again in Haskell it's called bind, the composer takes a monadic value and composes it with a monadic function. And together you can form a chain of monadic functions. Each of them returns a monadic value, and the composer changes it to the next. And this way you create a sequence of computation steps, and we'll see how all of them together can do something useful. So to make it more concrete, let's introduce a simple monad. I call it the square brackets monad. It implements a counter. So our monadic value is going to be the simple value x in the square brackets context, along with an integer. And this is our monadic function. It takes simple value x, returns a monadic value, y and k. And then this is the interesting part, the composer. And here I denote it as the name of the monad in a circle. So it takes a monadic value x and n, and composes it with a monadic function f. How does it do that? What is the composition rule for this particular monad? So it's going to take x and apply it into f, and then f is going to return y and k, and then the composer is going to take the k and add it to the original n. So it accumulates. So z would return 3 success, which means that we take the 3, pass it into f. F returns 4 success. We take the 4, pass that into g, and g returns error. At which point, the composition rule is not going to evaluate anything. It's not going to evaluate h in this case and just return error. Okay, so it works just like exceptions. Finally, how do we do I/O with just pure functions and pure values? So in this case, our context is going to be an operation, an I/O operation that's added to the simple value x. And that operation is going to be one of print, read, or no-op. There has to be a no-op because there are rules to which compositions are legal or not, but that we don't care about that for the moment. So how do we compose op(x) with f? So if op is print, the composition rule is going to print x to the console and evaluate f with no parameters. If op is read, the composition rule is going to ignore x, read a string from the console, and pass that into the next function in the chain, into f. And if op is no op, then we just take x and pass that into f. So what can we do with that? We have these 3 monadic functions, and we can compose them. So p is going to return print and what is your name. So the composer is going to print that to the console. Then R is going to get called with no arguments, and it's going to return read. So the composer is going to wait for input, and the user is going to input their name, and then the composer is going to pass the name to N, and N is going to return print hello and the name. My name is Ron Pressler. I'm the founder of Parallel Universe. We make an open source server-side stack for the JVM that helps you write very efficient applications. So the talk today is kind of messy. It's going to be part rant, part opinion, part some rehashing of old ideas. I am going to talk about functional programming and imperative programming. I am not going to discuss the relative merits of the two, but I am going to discuss the applicability of certain pure functional concepts for imperative languages, or rather lack thereof. And this entire talk is given from the perspective of an imperative programmer. So I'm not going to use the right names for things, or the names Haskell gives them. Yeah, we are going to discuss monads, and I'm going to explain what they are, and then why they're absolutely terrible. Not for imperative languages. For imperative languages, they're excellent for pure functional. Okay, so as a motivation, these are three classes from the JDK. This is a standard Java runtime library. Many of you must have heard that Java 8 now has lambdas. It also has, in the standard library, at least 3 monads. This means that there are more people using monads in production now in Java than anyone using Haskell for anything by probably orders of magnitude, which makes Java the most monad-heavy language in existence. Now, it's not just Java. Java itself, this is built into the libraries, but there's a very good family of libraries called ReactiveX that's based on monads for various languages. Their promises are based on monads in JavaScript, and recently I think Facebook introduced C++ futures, which are the same idea for C++. Okay, so we'll start by first going back to basics and defining a pure function. So a pure function is a subroutine that behaves like a mathematical function, which means that its only inputs are its arguments, and its only output is its return value, and it's not allowed to change any externally observable state or do any I/O whatsoever. Just takes parameters, compute results. Unfortunately, we have a lot to cover. Keep your questions to the end. I hope we'll have time because there's a lot to go through, and the best part is in the end. Okay, so pure functional languages means that all of our subroutines are pure. And as a consequence of this, or the converse, is that if you are not pure, then you are imperative. Even functional languages like Clojure, Erlang, Scheme, ML even, are imperative. So in this, I'm going to treat them as imperative. We'll see why. But an imperative programmer can then ask themselves, then if all of my subroutines are pure functions, how can I do anything useful? If none of them is allowed to do any I/O, how can I achieve anything useful? And monads is the answer to that. So monads are what gives